N-echelon folds. These are folds in a series at an angle to each other, similar to the other N-echelon things we've seen before, veins and joints and so forth. So we can have small scale N-echelon folds, and we can have very large scale N-echelon folds. And we can have superposed folding. Easy to slip and say superimposed because we're putting one on top of another, but the term is superposed, based on this principle of superposition on top of one another. So if we look from the left to the right, we see our first set of folds. These are recumbent chevron folds. And then we see in B some superposed folds. And we can see some fractures, some cleavage fractures that occurred because of that superposed folding. Now, image C is zooming in on a part of image B, and we're in close enough now that we don't see that overarching folding that was in part A. We just see one limb from A that's been folded. So we wouldn't necessarily know that this was a superposed folding system, except we have all those cleavage fractures. That tells us, even if we can't see the larger folds, that we have superposed folds. In 3D, we can have these superposed folds in multiple orientations. The basics fall into these four type categories: type 0, 1, 2, and 3. Type 0 is the folds are in the same orientation. This is basically like waveform interaction. Because they're in the exact same orientation, they just enhance each other, and the result is a bigger fold facing the exact same way as the original fold. Type 1 is the new fold is at 90 degrees to the original fold. They're both upright though. And so then you get this kind of cool hilly looking surface. Type 2 is where the first fold is recumbent and the second fold is upright and at 90 degrees. And you get this really funky, cool looking shape. And then type 3 is recumbent for the initial fold and upright for the second fold, but at 90 degrees from type 2, so that basically they're at the same orientation as each other now. Just the first one's recumbent and the second one's upright. And you get this cool pattern that looks exactly like what we were looking at on the previous slide. Now, in the real world, not everything happens at 90 degrees. So you can have any angle, and you can have more than two folds superposed on top of each other. However, this gives you a basic framework for discussing what's going on. So, go ahead, name your fold, like I said earlier. Then there'll be a place in Blackboard starting tonight for you to either submit a scan or a good photo. Make sure I can see the fold and read the writing. If there's too much glare or it's washed out, redo it. If I can't see it or read it, I can't grade it. I can't give you points. And the way it'll be graded is 5 points for following the directions for your drawing and 5 points for naming it properly. And I do give partial credit, of course. The last thing I want to talk about really briefly, just to expose you to it, are these strain patterns. You can have folds that look approximately the same as an overall shape, but the rock within that fold can be strained very differently. And you can see this if the rock had lots of polka dots, or if there are things within the rock that you can see the distortion. Kind of like we were looking at in the labs with the Moore circles. If there are concretions or other things you can see, then depending where they are in the fold and what strain pattern that particular fold has, you'll get different distortion. Now, terminology, a neutral surface is where in the fold there's no distortion. So it could be something like this one on the right, where as long as you're in the dead center of the layer anywhere along the way, that's where it's neutral. It goes, switches between squishing vertically to squishing horizontally, so at the dead center, it's stable. Or it could be like the one on the left, where right along the hinges is where there's little or no distortion, and anywhere along the limbs there's a lot of distortion. There are other possibilities as well. You can see a bunch of these strain patterns in the textbook, but that's what these circles and ellipses and other odd shapes are representing, is what the strain is like right in that part of the rock in that fold. With that, that completes today's lecture.